Thank you very much. I'm delighted to be here and talk to you about pavement-vehicle interaction, and in particular, how the smoothness and stiffness of our pavements play a role in fuel consumption. And a big reason that we're talking about this is that it's basically about trying to lower greenhouse gas emissions in the transportation sector, which hold on a second. Which are significant, right? Over 200 billion gallons of fuel in 2019, and this is about a third of the U.S. greenhouse gas emissions. So most of the U.S. Carbon dioxide emissions are coming from fossil fuel combustion, and what you can see is that out of those fossil fuel combustion, most of it is coming from that transportation sector, right? So when it comes to lowering our greenhouse gas emissions, we really have to focus on that transportation sector. Now, so even if we do just a 1% reduction in transportation emissions, that's 18 million metric tons of CO2 saved, right? So we're going to need every effort we can get to lower those emissions. And some of the targets that we've talked about in the context of like the Paris Accord agreements are about 65% reduction by 2050. So we're going to need a lot. Now, what we're going to be talking about today is basically what are some strategies related to vehicles, right? So obviously when it comes to the trucks, like we just heard about, there's a few different engineering related strategies we can use. And most of them are about the rolling efficiency of the vehicle, but we can obviously improve the energy efficiency of the engine. We can improve the aerodynamics. But another thing that we can do that people don't think about very much is reducing rolling resistance. And that will include the tires, but it's also going to include pavement vehicle interaction. Okay, so that's from the engineering side, but also from the policy side, you know, there are all kinds of different initiatives. You've probably heard of CAFE to try to improve our transportation carbon management. But the question that I want to ask is, what about fuel efficiency standards for pavements, right? We obviously don't usually think about fuel efficiency in the context of pavements. We think about it in the context of vehicles. But I'm going to talk to you about today is this pavement vehicle interaction, how our pavements actually impact the fuel consumption of our vehicles. So this pavement vehicle interaction, it involves a couple different mechanisms. The two that I'm going to talk to you about today are deflection and roughness. And roughness is basically when you're driving over a bumpy road, there's additional energy dissipation in the shock absorber system of the vehicle. And so additional fuel has to be consumed in order to overcome that. Pavement deflection primarily happens with very heavy vehicles like trucks, where it creates a slight indentation in the pavement such that it's continuously driving up a very shallow hill. And so this leads to what we call excess fuel consumption, meaning that there's a certain amount of fuel required to move the vehicle forward. This is an additional amount that's required to overcome either the deflection or roughness. And so what we do in our modeling is we quantify the amount of deflection and roughness that's occurring on a pavement, then quantify excess fuel consumption, and then use that to quantify either the economic cost of that additional fuel or environmental impacts. The roughness one probably makes sense to you. The deflection one might seem a little bit strange, but for those of you who are in Florida are used to probably walking or running on beaches, you know, and it's a similar analogy that, and there's actually been some research been done that walking on sand requires, you know, 2 to 3 times more energy expenditure than walking on a hard surface like a pavement, whereas running it's 1.6. So basically when you have more deflection, there's more energy dissipation, and that's the same thing with our pavements. All right, so the question I want to explore today is how can we design and maintain our pavements to be more fuel efficient. And what we really try and do in the hub is to use a life cycle perspective and to quantify both costs and environmental impacts of pavements. And this means that we start from, we call it the cradle to grave, or cradle to cradle if you're reusing those materials. But we start with materials production, and these are all different things you can do to lower those life cycle costs and environmental impacts. And then design and construction. If we can design pavements such that they use less material or last longer, that can be a benefit. The use phase, I'm going to talk about anything you can do to reduce that vehicle fuel consumption. We got a whole other set of research on reducing heat island effects. And then lastly, anything that we can do at end of life to enable material recovery. So we have some models that we've created to conduct life cycle assessment that basically quantify all these environmental impacts. And in the case of greenhouse gas emissions, we basically quantify what are those emissions throughout all these different stages of the life cycle. So there's, in the 11 years that the hub has existed, there's been a whole bunch of different PVI related research activities, including developing new models. We've even done some benchtop experiments to validate those. And then we've taken those models and implemented them to look at what's the impact of PVI on individual project decisions, then also looked at what's the impact of PVI when you're doing more network level decisions, and lastly, you'll hear about a new effort that we have on crowdsourced data collection. So because of the limited time, I'm going to skip over the model part and would be glad to catch up on that or talk about it in the Q&A, and instead I'm going to jump straight to some of these other things here. All right, so what I also want to do is start out to tell you, even before I get started, what are some of our key research findings? The first thing is that we can quantify excess fuel consumption due to PVI, and that may seem like an obvious thing, but believe it or not, it was considered pretty controversial for many different years. The second thing is we found that excess fuel consumption can be significant, but it's also context dependent. It depends on location and a variety of other factors. Surface and structure matter. That means that both roughness or smoothness on the surface matters, but also the structure of the pavement, which contributes to stiffness, matters. Excess fuel consumption can be used to improve design and maintenance decisions, and that's going to help us improve the fuel economy of the pavement network. And then also we can use crowdsourced data to transform asset management. All right, let me start with this first topic of project level implementation. And what this is showing right here is life cycle greenhouse gas emissions for urban interstate pavements in Missouri. And this is showing here for asphalt pavements and then concrete pavements. So those life cycle environmental impacts, one of the interesting things you might see is that, this is probably what a lot of people associate with environmental impacts of pavements, materials and construction, maintenance and rehabilitation. What you can see is that for both kinds of pavements, it's that use phase that really dominates here. And if we take a deeper dive into this is a breakdown of what's in the use phase, you can see it's excess fuel consumption due to roughness and deflection that's really driving the impacts for both kinds of pavements. Now, one of the things we found, this is for this specific example of Missouri, but the context really matters, and I'm going to give you some examples of that. First, the life cycle greenhouse gas emissions really depend on what the traffic level is. So these three types of roads show increasing levels of traffic. And like, for example, for lower traffic roads, the materials and construction is what really dominates the life cycle. Whereas once you get to the interstates, then that use phase really dominates the life cycle as we have more traffic. Okay, so traffic level matters. The other thing is that location can really influence the kind of impacts that we have. You can see that we did some studies where we looked at two warmer climates of Arizona and your state of Florida, and then also looked at Colorado and Missouri. And you'll notice that in the warmer environments, we have a higher use phase impact, and I'll dive into why that is in a little bit. The other thing that we see is that we had a pavement design firm come up with different pavements for those locations, both asphalt and concrete. And you can see how the type of pavement design that you use can impact the life cycle greenhouse gas emissions as well. Now, let's unpack a little bit what's different across those different locations. So as I mentioned, the design matters, like what kind of thickness you have and what were the different layers in the pavements. But also, if we dive into the use phase on these, what you can see is that the amount that comes from roughness, which is kind of like the darker mustard yellow, and the deflection, lighter mustard yellow, it really depends on the location. And in particular, what you see is that deflection matters a lot more in the warmer climates, for asphalt in particular. And that's primarily because asphalt's a viscoelastic material, which means that its stiffness is going to depend on what's the temperature in the location and also the speed at which the vehicles are driving on it. And so that's why we see a lot more of those, the impacts for asphalt pavements in those warmer climates, whereas it's not quite the same in the colder climates of Colorado and Missouri. So once again, that context matters. Pavement design, location, traffic level. That's why people say, you know, what's better, concrete or asphalt? I say it's really going to depend on all of those different factors. Okay, now I want to transition to more network level implementation. And what we've done is we've worked with several different DOTs to quantify excess fuel consumption on their pavement networks. This is showing a study we did for the state of Virginia, where we got data on all of their interstate pavements. And then from that, we're able to quantify what's excess fuel consumption in 1 year on all the different interstates. And what you'll see is that in the urban areas of Richmond and around DC, and then also along the coast here, that's where they have a lot of traffic. It's also where they have a lot of pavements that are in poor condition. And so that's where you see a lot more excess fuel consumption. And then we can also do is look at how those effects are over time and what is the driver of those different emissions. So what you can see is that roughness induced emissions from trucks are not that high. There's not as many trucks on the road, whereas there are a lot of cars on the road. So that's a big driver of roughness. On the deflection side, it's almost all trucks. Like cars just aren't heavy enough to really cause that much of a difference. So we can see a lot of those different effects right there. We did a similar study with the state of California, and what we see, this we did for all the Caltrans network. We got a lot of similar data, and once again, you see a lot of red spots around the urban areas. The other thing that we did, though, is that we were able to get data on all of the emissions associated with vehicles across the Caltrans network in terms of excess fuel consumption, but also CO2 emissions, NOx and particulate matter. And the interesting thing is that these are, even if you don't care about greenhouse gas emissions, these are air quality metrics that a lot of places are interested in as well. And what we could do is then estimate what percentage of these emissions were caused by PVI, right? And so you can see they range from 0.5% to about 4.5%, which may not seem by much, but as I mentioned at the beginning, even a 1% reduction of those transportation GHG emissions is significant. And also, you know, keep in mind, to lower all of the transportation emissions, you have to try to affect the behavior of millions and millions of people in California, get them to check their tires, to invest in more fuel efficient vehicles. Whereas this is really just about the DOT. So it's kind of easier to make change here when it comes to PVI. The last topic that I wanted to mention is, as I alluded to at the beginning, we have some work about crowdsourced data collection, and we've developed an app that's called Carbin, C-A-R-B-I-N, and you can download it from the Apple or Android App Store. And this is something that you just mount in your car, whether it be on your phone holder or somewhere on the dashboard, and it measures the vibrations in the car as you're driving. And what we do is then upload that anonymously to a server, and then we can quantify based on those vibrations what's the roughness in the road. And one of the neat things about this is that we've gotten a ton of data, you know, over 200,000 miles, 50 countries, you know, from a whole bunch of users. And you can go to this website right here, fixmyroad.us, to see sort of everywhere that we've been doing these measurements. And we have a lot of validation data to show how they compare to sort of more expensive measurements that are traditionally done. And we're not saying this should replace sort of the traditional way that transportation agencies conduct their measurements. This could be something that would supplement it because it's easy to do it on a frequent basis. And so we can use that to then help support decisions about improving the conditions of our roads and quantifying what those impacts would be. So just to summarize, once again, our research findings here, we can quantify excess fuel consumption. It's significant, but also depends on the context. Both the surface, the roughness component, and structure, deflection matter. And we can use that to improve design and maintenance decisions. And we can also use crowdsourced data to transform the way that we do asset management. And so with that, I'll say thank you. And here's where you can contact